Good evening friends. Today we will discuss the under excitation condition of a synchronous generator. Let's start from this figure. This is generator. Eg is induced EMF of the generator. Xd is synchronous reactance. V is terminal voltage of the generator. Xe is the system reactance, which is the sum of the GT reactance and the grid reactance. And ES is the system or grid voltage, and the angular separation between grid and induced EMF is delta. Delta is also known as load angle. For a steady state operation of a generator, the delta must be less than equal to 90 degree. So you all must have read in the book, if I will set delta at 90 degree, I am getting this equation. This is the equation of a circle. You can compare it with the equation of a circle, x minus a whole square plus y minus b whole square is equal to r square, where x and y are variables, a comma b is the center and r is the radius. You just compare here, x is similar to p, here a is 0, y is similar to q, and b is similar to this term, r is similar to this term. So let's plot this equation in the 2D plane, where x-axis stands for my P, active power, and y-axis stands for my reactive power. Let's plot this equation. So what is my center? P minus 0, 0, comma, this much. So my P is 0 and this is y coordinate. So this is my center, 0 comma v square by 2 1 by xe minus 1 by xd. So this is center of the circle, and what is radius? V square by 2 1 by xe plus 1 by xd. So this is the radius. Now I can draw a circle like this. Now as we are discussing only the negative part of the Q axis, means under excitation region, and we all know that the generator only acts in this positive P region. So I will consider only the 1/4 of the circle. Okay, let's forget about the remaining part of the circle. We will only focus on this line. This line is also known as steady state stability limit of the generator, because at this line my delta is equal to 90 degree. And also there is one thing, the capability curve of generator, it is provided by the manufacturer of the generator. So here I have shown the capability curve of the generator. You can see our generator has to operate within this curve. What will happen if the operating point of the generator crosses this line? This line is the under excitation limit of the generator in the capability curve. When our operating point is crossing this line, that means the huge amount of reactive power, it is coming from the grid into the generator. So there will be heating in the end region of the iron core of the stator winding. So for protecting our stator winding end regions, we have to operate our generator just below this line, means my reactive power absorbed should be less than the capability curve line. So what can I do for that? For that I have to set a limiter line. This is the limiter line. I have to set a limiter line in my automatic voltage regulator. Now here in this figure I have shown the steady state stability line far away from the capability curve. So for particular this condition, the pull-out curve value is higher than the capability curve under excitation line. So we have to see whether my pull-out curve is less than capability curve or more than capability curve. If my pull-out curve is more than the capability curve, then I have to set my limiter in such a way that it should be 90% of the capability curve line. 10% lesser than its limit. Okay. Now if I will set my limiter line as this, so my operating point of generator will never cross this line, so my stator end region iron heating will not be there, and also there is no chance of loss of synchronism because it will never cross this line also. Now how to set the AVR? There is a trick here. We have to consider 5 points in the active power line, 1, 2, 3, 4, 5, and the limiter, AVR limiter will ask for the settings for this 5 points. At this point of active power, how much Q you want to withstand. At this point, how much Q the generator can bear. At this point, so we have to put the values of Q. The desired Q we can put in the limiters. So these are the limiter settings. Now how to cross check whether our limiter it is correct, the limiter setting is correct or not. That can be verified from this equation. In the generator data sheet we are having XD value, we are having voltage level value of the generator, and this XC is XT plus XS. So XT we can get from the data sheet of the generator transformer, and XS we can get from the system data. The grid data we can get XS. So by putting all those values here and at different point of P, we can calculate our Q. So we can calculate this line Q. What is my pull-out curve Q? So I have to see whether the limiter setting it is more than pull-out curve or less than pull-out curve. And also I have to check whether the Q value in the limiter line is more than the capability curve line or less than capability line. So I can compare my limiter line with these two lines, and I can verify whether my limiter setting is correct or not. So I hope you all are clear with the minimum excitation limit of the generator. Thank you.